first time ever, an object from interstellar space has been observed to visit our solar system.
In the vastness of the universe, humanity has only scratched the surface of exploration. Despite our limited knowledge, we have long pondered the possibility of extraterrestrial life, often entertaining the idea that we might be alone in the cosmos. However, a paradigm-shifting event occurred with the arrival of our first interstellar visitor, Oumuamua. Unlike anything we had encountered before, this mysterious object left us in awe of the possibilities that lie beyond our world. Just recently, renowned astrophysicist deGrasse Tyson shocked the world by revealing never-seen-before declassified images of Oumuamua. What entities are responsible for sending this extraterrestrial messenger? What is the YORP effect, and what does it have to do with Oumuamua? Join us as we venture into the depths of space, propelled by the knowledge shared by none other than astrophysicist deGrasse Tyson, revealing the mystery behind this strange interstellar traveler. Back in 2017, a groundbreaking discovery was made that altered our perception of our place in the vast universe. Using the Pan-STARRS 1 telescope, Rob Warwick gazed deep into space and found an unusual object gliding through towards Earth. The visit of the mysterious flying object known as Oumuamua spurred a profound revolution in our perception of space and its vast possibilities. Despite its widespread popularity, our knowledge of this mysterious object has remained limited. In response to public interest, the renowned astrophysicist deGrasse Tyson has revealed previously undisclosed and highly classified images of Oumuamua. Leveraging his expertise, Tyson has shed light on this cosmic revelation, unveiling its profound implications for our solar system. However, before delving into the intricacies concealed within these long-guarded images, it is important to first explore the captivating nature of this mysterious celestial object, Oumuamua. On October 19, 2017, astronomers at the Haleakala Observatory, Hawaii, made the groundbreaking observation of what they initially believed to be a comet or an asteroid. However, further analysis revealed that it was, in fact, the first interstellar object ever detected within our solar system, excluding dust grains. The object's slanted orbit and rapid speed led scientists to conclude that it originated from beyond our solar system, prompting them to assign it the Hawaiian name Oumuamua, meaning a messenger from afar arriving first. Astronomers quickly realized that Oumuamua exhibited wild swings in brightness of up to 2·2 magnitudes that defied easy explanation. They soon inferred that it must have a highly elongated shape, with a length 5 to 10 times greater than its width. The strange shape of this mysterious flying object sparked many theories and hypotheses aimed at unraveling its origin and the purpose of the visit. One theory suggests that Oumuamua's elongated shape may result from tidal forces. When an object passes near a star, the gravitational forces exerted on it can cause significant stretching. This tidal stretching could account for Oumuamua's elongated cigar-like appearance. However, this explanation faces challenges in explaining the specific dimensions and proportions observed in Oumuamua. To gain further insights into Oumuamua's shape, astronomers have turned their attention to similar objects within our solar system. One such object is the asteroid 25143 Itokawa, which was visited by the Japanese Hayabusa spacecraft in 2005. Itokawa exhibits an elongated shape resembling a rough diamond or a potato. Studying Itokawa's shape and surface features has provided valuable information about the processes involved in forming and evolving such objects. However, while Itokawa shares some similarities with Oumuamua, the interstellar visitor remains distinct in its elongated proportions and lack of a tail. Oumuamua's remarkable acceleration, which is similar to a bicycle suddenly gaining speed without pedaling, adds an intriguing element to its nature. Upon entering our solar system from above the flat plane where planets orbit, it moved very close to the Sun, reaching approximately 1/4 of the Earth-Sun distance. Following this close encounter, the cosmic traveler continued its trajectory below the planetary plane. What is truly astonishing is that Oumuamua maintained an incredibly swift velocity, clocking in at around 196,000 miles per hour, indicative of a substantial amount of kinetic energy throughout its journey. To put this into perspective, its speed surpasses that of any human-launched object, including spacecraft and satellites. This high velocity has led to the hypothesis that Oumuamua may have originated from a binary star system. The theory proposes that gravitational interactions within binary star systems can eject objects at high velocities. If Oumuamua did indeed originate from such a system, it is plausible that the gravitational forces exerted by the stars propelled it on its interstellar voyage, accounting for its remarkable speed. Another possibility suggests that Oumuamua's velocity was a result of interactions with other celestial bodies in its home star system. Encounters with planets or other sizable objects could have acted as gravitational slingshots, propelling Oumuamua to its observed velocity. This mechanism is commonly utilized by space missions, leveraging the gravitational pull of planets during flybys to gain speed. However, further research is necessary to determine the likelihood of such encounters and their contribution to Oumuamua's velocity. But there's more to Oumuamua than just its speed. Studies have revealed fascinating details about its composition. It has a thick outer layer, similar to a cosmic shell, made of carbon-rich materials that solidified due to cosmic radiation during its extensive travels through interstellar space. Beneath this protective exterior, Oumuamua reveals its remarkably dense inner nature, primarily composed of rock and possibly containing elements of metal. What sets it apart is the absence of water or ice, which distinguishes it from typical comets or icy celestial bodies. Additionally, Oumuamua's surface has a reddish tint, resulting from prolonged exposure to cosmic rays over hundreds of millions of years. Scientists have also considered the possibility that Oumuamua's high speed is a consequence of its shape and composition. On the other hand, several individuals have requested for the contribution of renowned experts such as Neil deGrasse Tyson and Michio Kaku on the discussion around Oumuamua. Interestingly, Neil deGrasse Tyson refrained from commenting on the matter until substantial evidence and the recent declassified photos became available, leaving everyone eagerly anticipating his perspective on the subject. Some researchers suggest that the object's elongated form, as inferred from its light curve, indicates that it could be a fragment of a larger body. Suppose Oumuamua broke off from a larger object due to a collision or other violent events. In that case, it might have acquired a substantial velocity during the separation process. This would imply that Oumuamua's speed is not intrinsic to its nature, but rather a result of past events. Comets, for instance, traverse our solar system at varying velocities. While some comets can achieve speeds comparable to Oumuamua's, such as Comet Hale-Bopp, they typically exhibit residual gas and dust due to their volatile composition. In contrast, Oumuamua displayed no such characteristics, distinguishing it from known cometary objects. Another comparison can be made with asteroids, rocky objects that orbit the Sun. Most asteroids in our solar system move at significantly slower speeds than Oumuamua. For instance, the average orbital velocity of the well-known asteroid series is approximately 17,880 kilometers per hour, less than a fifth of Oumuamua's estimated speed. This disparity emphasizes the exceptional nature of Oumuamua's velocity and its distinction from familiar solar system objects. Here's where things become even more intriguing. Some experts speculate that Oumuamua could be more than a naturally occurring object. They suggest that it might be an artificially crafted creation meticulously made by an advanced extraterrestrial civilization. Aliens. Oumuamua may be part of an incredibly advanced alien spaceship or equipment designed for exploration. According to this theory, Oumuamua's unique features could serve multiple functions. Its elongated structure could enhance its resilience during interstellar travel. At the same time, its propulsion system could enable precise maneuvering through the cosmos. Popular figures like Avi Loeb, an Israeli-American theoretical physicist and astronomer, strongly believe this theory. Loeb even proposed a controversial hypothesis that Oumuamua could be of extraterrestrial origin, suggesting that it could be an artificial object or even a piece of alien technology. He argued that its peculiar properties, such as its elongated shape and unusual acceleration, could indicate an artificial origin. Loeb's hypothesis generated widespread discussion and debate within the scientific community. However, it is important to note that many scientists and astronomers have expressed skepticism about his claims. The prevailing view among most scientists is that Oumuamua is likely a natural object, such as a comet or an asteroid, with its unusual properties being the result of natural processes. Wesley C. Fraser and other researchers combined brightness measurements from multiple telescopes to investigate a rotation period. They concluded that no rotation period can account for the observed brightness variations. Instead, the object appears to be tumbling in an excited rotational state. This unusual, peculiar tumbling motion was unlike anything seen before. This irregular rotation has puzzled scientists since its discovery. Observations made by astronomers have provided valuable insights into Oumuamua's spin. It completes a full rotation every 7.3 hours, which is relatively fast compared to the rotational periods of other objects in our solar system. Additionally, its brightness varies significantly as it spins, indicating that different parts of the object reflect sunlight to varying degrees. This irregular rotation has perplexed scientists and led to various intriguing theories. One hypothesis proposed to explain Oumuamua's spin is the spin-induced outgassing theory. According to this idea, volatile substances beneath its surface are exposed to solar radiation as the object tumbles through space, causing it to vaporize and create tiny gas jets. These jets act as thrusters, imparting a torque on Oumuamua and causing it to spin irregularly. This implies that Oumuamua's composition may contain volatile materials susceptible to sublimation under the influence of solar radiation. However, further studies are needed to confirm if this mechanism is responsible for Oumuamua's peculiar rotation. Another theory suggests that Oumuamua's tumbling motion could result from a prior collision with another object. It is conceivable that a high-speed impact distorted its shape and set it into an irregular spin. This collision might have occurred in the object's home star system before being ejected into interstellar space. However, the exact nature of such a collision and the object involved remains speculative due to limited observational data. Detailed analysis of Oumuamua's shape, composition, and surface features could provide clues supporting this theory. To better context Oumuamua's peculiar movement, let's examine other celestial objects with similar behavior. One such object is the asteroid 4179 Toutatis. This elongated asteroid, discovered in 1989, displays a tumbling motion akin to Oumuamua. Scientists have proposed several theories to explain Toutatis's erratic rotation, including the YORP effect. According to this effect, sunlight exerts a torque on the object due to uneven thermal radiation. This torquing effect gradually alters the asteroid's rotation, leading to its irregular tumbling motion. While this mechanism could also apply to Oumuamua, its exact role remains uncertain. Interestingly, another comet, 67P/Churyumov-Gerasimenko, also showcases an irregular rotation. Researchers discovered 67P/Churyumov-Gerasimenko, often called 67P, on September 11, 1969. This comet orbits the Sun and exhibits a striking shape and distinct movement. It features two distinct lobes connected by a narrow neck, giving it a unique appearance often compared to a rubber duck or a bowling pin. Scientists have named the larger lobe body and the smaller one head. The comet's elliptical orbit completes one revolution around the Sun in approximately 6.45 years. It belongs to the Jupiter family of comets, indicating that its origin can be traced back to the Kuiper Belt, a region beyond Neptune populated by icy bodies. However, researchers believe that gravitational perturbations caused by Jupiter's immense gravity captured 67P into its current orbit. This previously studied comet undergoes various changes in velocity and distance from the Sun. In the case of Oumuamua, scientists believe that the outgassing of volatile substances from the comet's surface plays a significant role in its tumbling motion. As the ice on the comet's surface vaporizes under the influence of solar radiation, it creates localized jets that act like thrusters, altering the comet's rotation. The similarities between Oumuamua and these objects hint at potential underlying mechanisms responsible for their unusual spins. Further exploration and detailed analysis of these objects can provide valuable insights into the nature of Oumuamua. The origin of Oumuamua has also been a subject of great speculation. Some scientists propose that it could be a fragment of a larger body ejected from its home star system due to gravitational interactions or a catastrophic event. This ejection might have imparted an initial spin on Oumuamua, which has persisted throughout its interstellar journey. The exact process by which Oumuamua was ejected and its subsequent trajectory remains uncertain, highlighting the need for more data and further research. That's interesting. But there is a possibility that Oumuamua is a byproduct of a collision between two objects in a distant star system. The resulting debris could have been flung into interstellar space, with Oumuamua being one of the fragments caught in our solar system's gravitational pull. However, without further evidence, these theories remain speculative. Detailed analysis of Oumuamua's composition, isotopic ratios, and surface features could provide clues about its origin and shed light on the mechanisms involved in its peculiar spin and movement. As shown in these images, the absence of visible emissions baffled scientists even more. This exclusion of visible emission eliminated the possibility of Oumuamua being a typical comet or asteroid, and presented an intriguing puzzle that required further investigation. There is a possibility that Oumuamua's lack of emission could be explained by it being a dead comet. A typical comet's icy composition vaporizes as it approaches the sun, resulting in an emission trail. However, if Oumuamua had lost most of its volatile materials due to repeated close encounters with stars in its long interstellar journey, the absence of visible emission could be accounted for. Intense heat and radiation from these encounters may have stripped away Oumuamua's volatile components, leaving behind a rocky or metallic core without the usual cometary features. That gave room for the possibility that Oumuamua is an interstellar asteroid. If Oumuamua were an asteroid, the lack of visible emission could be explained, as asteroids typically do not exhibit the same outgassing behavior as comets. However, the elongated shape of Oumuamua remains a mystery, as asteroids in our solar system tend to have more irregular shapes. Some scientists propose that the elongated shape could result from gravitational distortions experienced during close encounters with a star or a planet in its parent star system. Similarly, asteroid Bennu, the target of NASA's OSIRIS-REx mission, provides an interesting comparison. Bennu, classified as a primitive carbonaceous asteroid, did not display any visible emission during its close encounters with Earth. However, this lack of visible emission was expected, as Bennu's composition was predominantly rocky, with minimal volatile content. This demonstrates that asteroids, unlike comets, generally do not exhibit visible emission, aligning with the notion that Oumuamua could be an interstellar asteroid. What were Neil deGrasse Tyson's views on the declassified images? Upon releasing the declassified images, Neil deGrasse Tyson assumed the responsibility of actively exploring and explaining the nuances and potential implications of Oumuamua. Neil deGrasse Tyson consistently emphasizes the importance of evidence-based inquiry in his discussions on Oumuamua. He highlights the need to approach the topic with skepticism while exploring the fascinating idea of Oumuamua as a message. This approach reflects the beauty of scientific exploration, where extraordinary hypotheses are considered, tested, and either validated or refuted. Tyson suggests the universe might be far more mysterious and intricate than our current comprehension. He also contemplates Oumuamua as a test that gauges our technological and scientific advancement. How we perceive, study, and react to Oumuamua could provide valuable data to its creators about our civilization's maturity and readiness for potential contact. This perspective extends beyond the object itself and raises broader questions about our technological and philosophical readiness to understand and interpret such phenomena. Tyson postulates that Oumuamua's sudden appearance and the subsequent scientific activity it triggered could be seen as a test of our technological capabilities. The fact that we could detect, track, and analyze it indicates our growing capabilities in space observation and research. Moreover, Oumuamua challenges our scientific paradigms with its unusual acceleration, unique shape, and trajectory that defy easy explanation. Tyson sees this as a test of our scientific flexibility. Can we adapt our theories and models to accommodate this new data, or will we try to force it into pre-existing frameworks? Oumuamua's brief passage through our solar system required rapid, coordinated efforts from the global scientific community. Tyson sees this as a test of our ability to collaborate, share data, and pool resources in the face of a sudden and unexpected cosmic event. It raises the question of how we performed in this test and what lessons we have learned to prepare for future interstellar visitors. Delving deeper into the test hypothesis, Tyson speculates on the broader message behind Oumuamua. If it was deliberately sent our way, perhaps the test is not just about detection, but interpretation. Can we understand a message or signal embedded in its structure or behavior? And if so, how do we respond? These questions remain unanswered, and the search for answers continues. Another perspective Tyson explores is the idea of Oumuamua as an interstellar emissary. Instead of being a mere probe or artifact, could it be a vessel carrying representatives from a distant star system? While this theory may seem like science fiction, Tyson argues that we must consider all possibilities, no matter how outlandish they might seem. After all, the universe is vast, ancient, and full of wonders yet to be discovered. Tyson's contemplation of Oumuamua as either an interstellar emissary or a mere cosmic coincidence demonstrates the depth of his scientific inquiry. His approach blends wonder, skepticism, and rigorous scientific analysis. It challenges our understanding of life in the universe, the nature of celestial objects, and our place in the cosmic tapestry. The implications of Tyson's theories are vast, ranging from technological advancements to philosophical introspections. They disrupt conventional astrophysical theories and potentially reshape our understanding of the cosmos. If any of his theories hold, it would mark a significant paradigm shift and propel us into a new era of space exploration. Thanks for watching. Check out the video you see on your screen right now. It's unbelievable